Welcome to our channel for probability and statistics. In this video, we will talk about hypothesis testing of the difference of population means using paired observations. So we know if we want to test the population mean difference, usually we take random samples from both populations and calculate the sample means for each sample. And the sample size may be different, right? But sometimes we can also use the so-called paired observations or paired experimental design, which means we take the same unit, say for example 20 units, then we apply two different experiments or treatments. So these two treatments can be called populations. So two populations or two treatments assigned randomly for homogeneous units. So each unit will take each of these two treatments. Then we get the data and calculate the difference for each observations based on the paired tests. So we say this is paired observations. So actually these paired observations like one sample because each unit gets two treatments and we take the difference for each treatment to each two treatments, right? So this is like a same unit and this is the one sample. So this is called paired observations to test the difference population means. And from the sample we can get the test statistic T, which is the mean of the difference, then minus the hypothesis the population mean difference, then divided by the square root of the sample difference, divided by the square root of the sample size. So this statistic has followed a t-distribution with n-1 degrees of freedom. So if we form the null hypothesis or H0 that the population treatment difference equals hypothesis the value D0, then if we calculate the test statistic T, if the T located in this critical region, then the test is significant. Say we will reject this hypothesis. So next we show an example using paired t-test. So this sample is based on the blood sample data in a study conducted in the Department of Forest Resource and Environmental Conservation at Virginia Tech. Wilson examined the influence of the drug succinylcholine on the circulation levels of androgens in the blood, and the blood samples were taken from wild free-ranging deer immediately after they had received an intramuscular injection of succinylcholine administered using darts and a capture gun. And a second blood sample was obtained from each deer 30 minutes after the first sample. So after each the deer was released, and the levels of androgens at time of capture and 30 minutes later measured in nanograms per milliliter for 15 deers are given in the table. Assuming that the populations of androgens levels at time of injection and 30 minutes later are normally distributed, and the test at the 0.05 level of significance whether the androgen concentrations are altered after 30 minutes. So this sample includes 15 deer, and each deer we get two data. One is the blood level for the injection, and another data is the 30 minutes after it, right? So this is the sample data, 15 deer, 15 observations, and each has a paired data. One is blood level is the time of injection, and second data is the 30 minutes after injection. Then for each DI, we calculate the difference called DI. So DI has 15 observations. So this DI is like one sample, one population data, right? So the solution is we let mu1 and mu2 be the average androgen concentration at the time of injection and 30 minutes later. So we form the hypothesis. For the null hypothesis, H0 is mu1 equals mu2. Or say the mu D is 0. So mu1 minus mu2 is 0. This is the hypothesis for null hypothesis, what we want to test. And the alternative hypothesis, H1, is that we will reject H0, which means mu1 not equal to mu2. Or say their difference is not 0, right? So the test significant level is 0.05. And the critical region is T larger than 2.145 or T less than minus 2.145 at 14 degrees of freedom. So the computation for the sample is sample mean, and the standard deviation for the DI is 9.848 and 18.474. So this comes from this table, from this column. So we calculate the mean of this data, this column. So this is the DI bar, right? Then also calculate the sample standard deviation of this data. So we have both mu, D, and SD on hand. Then we can fill in the form to calculate the test statistic. So we just fill in the mean, difference, and standard deviation and sample size. So here 0 is because we tested these two difference is 0. So we just fill in 0 here. So if say we want to test if mu1 minus mu2 is 5, so we have to fill in 5 here, right? So this is from the sample. Sample T statistic is 2.606. So although this 2.06 is not in the critical region, because critical region either T larger than 2.145 or less than minus 2.145. So 2.06 not in this region. But we calculate the p-value. T statistic larger than 2.06 is about 0.06. So you can see, although this value not in critical region and this is larger than 0.05, but it's very close, it's in the margin. So in this sample, we can say there's some evidence that there is a difference in mean circulating levels of androgen. There's somewhat has some evidence, right? Because the sample is random, maybe we take from other samples or take more than such samples many times. So some part of them may have significance, right? This is the conclusion of this example. Thanks for watching.